Hello everyone. So in this video I'm going to implement a feed-forward type neural network for the MNIST dataset. So the MNIST dataset is a freely available dataset with 70,000 handwritten digits, and this is an open source dataset, American based dataset. So this includes 70,000, as I mentioned, 70,000 handwritten digits. So the scanned versions of 70,000 handwritten digits. So this is a inbuilt dataset coming with Keras. Actually it's not installed with Keras, but you can download directly using Keras. The MNIST dataset can be directly downloaded from Keras. So it's like an inbuilt dataset of the Keras module. What we have to do, we have to load the dataset. So at the initial time, if you are loading it for the first time, it will be downloaded, and then it will be stored in your computer. Then you can later use it anytime you want, right? Okay, so let us first get the dataset from the we can download it. So we can use the Keras datasets import MNIST. So this is, as I mentioned, the inbuilt dataset available in MNIST. So what happens here now, if you are running this for the first time, this will be downloaded from Keras database and installed in your computer, stored in your computer, right? So in my case, I have this already downloaded, so it will be there in my case. In your case, probably you will download it at this time. Automatically download, it will be automatically download. So we can directly get the train data and test data separately to the data set. To these train data, train target, test data, and test target, like this. Test data and test target. Okay, so what we have to do is MNIST.load data, right? So you can run this, right? And let's see the shapes, right? So these are loading into NumPy arrays, as we already know. So we can see the dimensions of these arrays, and probably you can then understand what are their train data.shape and test data.shape. And right, so the train target.shape and test target.shape. Right, so you can see now it says 60,000 28 by 28 images, 10,000 20 by 20 by 20 images in test data, and target contains 6,000 and 10,000 images. So let me show you one image of this data set. Let's see the first image of the training data. So you can use the matplotlib library to view that. From matplotlib import pyplot as plt, and we can use the plt.imshow to view. Let's view the first image. So we have 60,000 image. We are going to see the first image, and I will use the color map binary, so you can use it as a gray image, and then plt.show, right? So we run this, and you are going to see output like this, right? So this is the image, as I mentioned earlier, right? So this is the first image. So you can guess what they are in the test target one, right? So the target of this image should be there. So the label, so it will be like simply 5. Sorry, we have to check the train target, right? So this is the train data 0 and train target 0. It contains 5, as we expected. And this is what actually happens. Now we are going to train and evaluate and test a feed-forward type neural network to identify handwritten digits using the MNIST dataset. Now each digit is contain a gray value. So this is a gray, not a color image. This is a gray, so it's having a value in between 0 to 255, and like you can have the gray value for each pixel. And in this data set we have like each pixel is a 8-bit number, as I mentioned, which is having a pixel range in between 0 to 255. And this is all the images are like 28 by 28 images, not like 7 by 7. It is 28 by 28 images, as you can see here, 28 by 28. So like you have 781 pixels available here, 784 pixels available for each image, right? And this is like the data. So we have in the data, like we have 60,000 in test data and 10,000 in test target. And in the targets we are having like basically the label of these each image, right? So then we can we have the training data and testing data separately, 60,000 and 10,000. So we have the corresponding targets as well. Yes. So what we are going to do now, we have the data, the training data and testing data. So what we can do now, yes, so now we will build up a neural network for this problem, right? So let me use as in the previous lab session or the practical session, I will use the sequential model, and also from I will use the dense layers, import the dense layers, the fully connected layer type, you can remember. And additionally, I'm going to import a new layer type called flatten. This is required. And let me create a new let me create a new sequential type empty neural network model, and I'm going to like add the first layer. Now, as I mentioned in the practical session, now usually we are not going to mention about the input layer, but here we have to, since we are going to apply this image, a 2D image, right, a 2D image to the neural network, but we can't directly do that. What we have to do, we have to flatten the image like this. So flattening in the sense like we are taking row by row and flattening this image, right? So finally it will be like having 784 and let's say one row and 784 columns. So flattening, right? So we are taking row by row and flattening it up. So what we are going to get, like we are going to get 1 into 784, right? So we have like 28 into 28, so it will be like 784. So one row and 784 columns, or else like 784 rows and one column, right? So we are going to flatten it up. So in order to do that, what we can do, we can have a flatten layer here. So flatten layer is not going to do that much a thing. So what it's going to do, like it's going to take an image, the image that we are going to input to that neural network, and do this operation, right? So it's going to flatten it up and like create a neuron, 784 neurons, right? So that's what it's going to do. It's going to convert the pixels into like a flattened layer, convert the 2D image into flattened layer. So we can have the like first layer neuron, 784 neurons for the first layer, right? So we can do it like yeah, so we can have the flattened layer. What we have to mention, we have to mention the input shape, the shape of the input images, right? So what are the images that we are going to input, the size should be mentioned here. So we are inputting a 28 by 28 image, right? So what the flatten layer is going to do, it's going to take the image and flatten it up, right? It's going to convert it and flatten it up, right? Okay, so yes, so then what we can do, like, so this will be the first layer, I mean the input layer, and then what we can do, we can add the hidden layers here. the general hidden layers. So we can use the dense, and I will add like 512 neurons, right? 512 neurons with the activation of ReLU. Now you may wonder whether we need to like have the input shape. Not necessary. You can now have this as this as well. Okay, so then another layer. Let me add another layer, which 256 neurons, and another layer like with 128, and another layer. So I'm just randomly adding those layers, right? No theory behind, as I mentioned earlier. Then finally, how many layers should be there? 10 neurons at the output layer, since we have like, this is a classification problem and we have 10 categories, 0, 1, 2, 3, like up to 9. So we have 10 categories, right? Then probably we have to like compile the model. So we have to use like model.compile and mention the few parameters like the loss function, so categorical cross entropy, and the optimizer, we will use the Adam optimizer. We can use the Adam optimizer here, and the metrics we can like visualize the accuracy, right, while training of the neural network. If you are like going to put accuracy here, so it will show us the accuracy while training the neural network. And the model.summary, we can double check the neural network architecture from here, right? So you can leave, like we have like 500,000 parameters, a big neural network, right? 500,000. Now you can see now here weights are there like 512 into 256, and here 784 to 512. So lots of parameters are there, right? Not necessary, but I just wanted to like show you this implementation. That's it, right? I mean, we can always use a simpler neural network for this as well, but since we have like 784 pixels as the input, we will use like layers having comparatively large number of neurons. Okay, so what we can do, we have to do the categorical conversion, right? So from keras.utils import nputils, as we did in the last practical session. So I will get new train data, sorry, new train target. Actually we have to convert the target using np.utils to categorical. And so we are going to apply the train target, and it will be converted to the categorical form. So we have to do the same thing for the testing data as well, right? So test target, for the test, actually the test target, yes, yeah. Okay, so we have converted it. Now probably if you want to see what happened here, I will print the train data before the conversion, right? The first 10 values of the first 10 rows of the train data before the conversion, and after the conversion, the new train target, the first 10 values. So you can see like it's 5 0, like likewise. So these are the corresponding categorical form of those things, right? Okay, then what we can do, one important thing now, you can have this idea, each pixel contains a value between 0 to 255. Usually we are not going to apply these big values to neural networks, so we are always trying to normalize it and scale down it. So in order to scale down this, we are going to like divide the data, right, from 255, right? So you can probably understand what's going to happen. Now dividing 255, so what will happen, you know that these are numpy arrays, so we are dividing 255, so all the pixels will be divided by 255, both the test and the training data. So what's going to happen now, earlier it had a range of the pixel had a range of 0 to 255, right? 0 to 255. So we are going to divide all the pixels by 255. So what's going to happen now, let's say the minimum value of the pixel 0, the minimum value it can have in a image is 0, so 0 divided by 255 will be 0. So the maximum value a pixel can have is 255, so 255 divided by 255 1. So basically this is going to convert the pixel which has a range of like 0 to 255 into 0 to 1. So we have like simply normalized the images to have a range in between 0 and 1 instead of having a range between 0 and 255. So that's what we are going to do here. And then what we can do, we can then use the model.fit command, model.fit, and train data, train target, right? Train data and train target. So let's mention the number of epochs. So we will use it for like 20 epochs, let's say, right? So we will train this and we have an error, but yeah, so we have like provide the new train data and the converted, right, new train target. So then probably it will take it will train. Now you can see it takes a considerable amount of time. Now for a single epoch like 20 minutes, 20 seconds, since yeah, I think we have some kind of a issue while training the neural network. Yeah, so this is the issue. Now last layer we have to use the softmax, right? Okay, now probably this will work. Yeah, so the accuracy you can see, and the loss is decreasing and the accuracy is increasing, right? So meanwhile let me plot the graphs. From matplotlib import pyplot as vlt, right? And plot the model.history the loss, we have to visualize the loss, and yeah, so then the x label and the y label. Right, so similarly we can plot the accuracy as well. Yes, accuracy as well, and so this will be the accuracy, right? Yes, so that's it. And also we can evaluate the model. New test data and new test target, so we can evaluate the model as well. And yeah, so that's it about this. And another important thing, now you know that in a neural network, what's the most important thing? The trainable parameters, right? So we are adjusting the trainable parameters, and somehow we are trying to converge the neural network. That means obtain the weights and biases, the values for the weights and biases, which gives us the minimum possible loss. That's what you call the convergence, right? So the most important thing when we are like training the neural network, the weights and biases, so that's the knowledge, right? So we know that we are using like 60,000 images to train this neural network, but doesn't matter the weight, the weights and biases. So the knowledge that we are going to take from those training images are saved in the weights and biases. So it's like this. Now if we can like read 1,000 books and get the knowledge of that 1000 books, right? So we don't need to have the 1000 images, 1000 books, right? So it can be like we can fill a room with that 1000 books, but right, so that's not the important thing. So we have the knowledge in our brain, so it's like equals to the knowledge of these 1000 books, right? So similarly, in a neural network, no matter how many images that you are going to use, how many data points that you are going to use to train the neural network, the most important thing is the knowledge gained. Now the knowledge gained is saved in the weights and biases, right? So what we can do, we can save that model into a physical file. So that's the most important thing. So after training a neural network, we can save it to a physical file, and that will be saved. So what we can do, like we can take it we can save it to a physical file, and then we can deploy it in a mobile application, web application, cloud servers, anywhere you want, right? So that's the knowledge that you are going to take and you are going to save it. Now it's like we are like, let's say if you can save a physical file of our brain, and after our death, if we can like use it somewhere else, if we can plug it for some other one, right? So similar kind of thing. Now you can see this is optimized quite well, and the accuracy is reached like almost 100%, right? So let's do the evaluation. So it's given like testing accuracy of 98 and testing loss of 0.01, and this is how we are going to save the model weights. Save weights, FNN MNIST dot H5. So we are going to save the neural networks in H5 format, right? So after running this, the knowledge that you gained from the knowledge that the neural network gained from this 60,000 image of training will be saved to a physical file. You can check in your working directory, this is saved as a H5 file, right? Okay, so I will quickly go through some other thing as well. So this is the code that we implemented in the practical session, right? I want to show you something here. Probably I will run it again, and yes, so what I need to show you that we can visualize the weights and biases, the trained weights and biases of the neural network. So quite simply, what we have to do for layer in model dot layers, right? So what will happen, this loop will run like the number of times, which equals to your layers, the number of layers in your neural network, and each of the time what we can do, we can get the weights. Let's say parameters equal layer dot get weights. So let me print the parameters and check. Yeah, so you can see these are the trainable parameters, or the weights and biases. So the thing is, actually this has two main things now for each layer. So I will put a separator, so then we can identify each each layer, right? So this is running for layer by layer, as I mentioned. So if you put a separator, so you can definitely see the layers. Now this is the first layer, this is the second layer, and this is the third layer, and this is the fourth layer likewise. Now in each layer you can see how we can get we have like two main things, right? So these are weights and these are biases, right? Weights and biases. So what we can do, we can take those things separately. Let me get the weights equal, so we have like two elements in this parameters array. So the 0 element is this section, so which contains the weights, and the biases will be there in the 1. So that means this second array, right? So parameters are both of these two, and parameter 0 will be this one, parameters 1 will be this one. So what we can do, I will print those separately. Weights and biases, like this. So each layer we can yes. So then let me add, yeah, so I will put a separator at the top as well, so you can clearly see the weights and biases, right? So these are the weights of the first layer and the biases of the first layer. Now can you see, imagine now how many weights should be there in the first layer? So it's like this, right? Like we have 8 into 4, right? So 32 weights should be there. And how many biases? Since we have 8 neurons, so there will be like 8 biases, right? So let's see. So these are the, I think 32 weights are there and 8 biases are here. So this is how we are going to visualize the weights and biases. And the other thing is that you can check the number of neurons in the other layers, the weights and the biases as well, right? So this is how we are going to visualize the weights. So these are the optimal weights and biases that the neural network has obtained, right? So I mean, we are going to do lots of things using these things, the weights, trainable weights and biases. So I mean, there's always a reason of showing these weights and biases to you. We can do lots of things using these weights and biases. And also this is important, how to save a model in Keras. So we will use them in like mobile applications, web applications. We can use it everywhere, right? So the most important thing, after training a neural network, we can save it to a physical file. So this is the knowledge gained, right? Okay, so with that, I'm going to conclude this session, and thank you very much. And please go through the video and try to implement these codes and try to run these codes and check the results. Thank you very much. So we will meet with convolutional neural networks and more knowledge on the coming weeks. Thank you very much.